See a little countdown clock here, and then you'll be live.
Cool.
Okay, go.
Hello, everyone. Um, Today, Vanu and I are here to talk a little bit more about um, our experience with the American Rocketry Challenge and how we won it in 2022.
Yeah, so I'm Vanu. Currently, I'm a student at the University of Washington. I'm studying mechanical engineering, and I competed in the American Rocketry Challenge from 2019 to 2023.
And I'm Shreyas. I am currently at Georgia Tech pursuing aerospace engineering, and I competed in the American Rocketry Challenge from 2021 to 2023. And both of us represented Newport High School out of Bellevue, Washington.
Yeah, uh, so feel free to ask questions at any time. Just pop them in the chat, and yeah, we'll try to answer them as we can. So why should you listen to us about ARC, basically? Well, back in 2020, when there was no launch contest because of COVID, my team won the presentation competition. And in 2022, our team won the launch contest and we placed second at the International Rocketry Contest.
Yeah, so you may be wondering what the American Rocketry Challenge entails in general. So ARC is the largest rocketry contest in the world. Essentially, competitors are given a time target, so a flight duration, time window, and an altitude target. Um, and you are also given stringent guidelines for how to design your rocket, which we'll get into on the next slide. Um, but basically, you score points the further away you are from the time target and the altitude target. So it's 4 points per second you are off the time target, and a point per foot you are off the altitude target. So yeah.
Yeah, so in 2022, the target altitude was 835 feet for the qualifications. And then at the national competition, they switch it up a little bit. They have two altitude targets for two different launches, 25 feet under that and 25 feet over that. So 810 feet and 860 feet. The flight duration was 41 to 44 seconds. So if you're in that time range, you get no points for time. And of course, points are bad here. And then for the rocket guidelines, the twist in 2022 was that you have to use body tubes of two different diameters. So whether that's a larger payload section and a smaller booster section or the other way around, either way is fine, but your body tubes need to have two different diameters. A general requirement that is pretty much always there is your rocket has to be longer than 650 millimeters and lighter than 650 grams. That's just to keep the competition equal for everyone. The one tube has to be the payload section, the other tube has to be the booster section, and the payload is two eggs. Those are your passengers, so they have to be intact after your flight. And another twist was that the eggs had to be oriented sideways inside the payload section. And that's interesting because when they're sideways inside a casing, they actually won't fit inside the standard BT70 or 60 body tubes. They will actually only fit in the BT80 size body tubes.
Yeah, so now we'll get a little bit more technical and talk about the designing process of our rocket. The main software we used was OpenRocket, not only to design our rocket, but also run like basic simulations to see what the apogee altitude would be and things of that sort.
Yeah, so in our design process, we start out with a whole bunch of prototypes, varying basically any parameter we can. And we just start to narrow in on what exactly we want a rocket to be. So here are some examples of some prototypes and a version closer to the final rocket that we had. So some of the factors that we consider are mass distribution, which is a huge one. For example, that means where we place the ballast and also where we place the altimeter. You can see in the top model, the altimeter is inside the nose cone, and in the bottom two, the altimeter is inside the transition. And again, those impact the center of gravity, where it is in the rocket, pretty strongly. Another factor we like to change is the length of the rocket. And that's important because the length of the rocket gives us a lot of control over where we can put the CG and CP. And of course, that leads us to stability, which we can change the CP with mostly the fins. So how big they are and how far up on the rocket body they are. The bigger the fins, the farther back the CP is, and therefore the higher our stability margin will be as well. And we always aim for a stability margin of between 1 and 2, where stability is the distance between the center of gravity and the center of pressure divided by the diameter of your rocket. And 1.2 or 1 to 2 is generally a good range so that your fins can correct for the wind without weathercocking and overcorrecting. Yeah, so we come up with these different designs. We simulate them with different motors depending on the mass of the different prototypes. You can see in the top one, it's 520-ish grams. The second one is about like 480, I think. So you definitely need different motors there to reach around the right altitude you want. And in the final one, we basically set up all the best parts of every prototype, and then we start building. So in the building process, 3D printing is one of our most vital technologies. It really, honestly, is probably the biggest contributor to our success in the technical department. First of all, it's extremely versatile, and you can rapidly prototype pretty much any component you want. For example, on the right here is our altimeter sled. You can see it started out as just a simple pin-based mechanism where you just slot it into a body tube and put a pin through it, and it's supposed to stay there. But it gradually evolved to institute a thread and screw system where threads are epoxied onto that body tube, and that just makes it much more easily replaceable and a lot better. So 3D printing often happens alongside a CAD program, and my program of choice was Fusion 360. But 3D printing is not without its limitations, one of the biggest of which is anisotropy. So when a material is anisotropic, that means its material properties in one direction are different than another direction. And in the case of 3D printed parts, because they're built up layer by layer, they are weaker along the layer lines than perpendicular to them. So what that means for how you design or tweak models for 3D printing, for example, our fins, which I'll show you a picture on the next slide, we print them on their leading edge. And that is basically to mitigate any of the impacts they receive on landing to be in their strong direction rather than their weak direction. And that was a problem we had faced in previous seasons, where if you print them like triangular or trapezoidal base down, they actually are prone to snapping on landing, which obviously we don't want that. Another limitation of 3D printing is size, because you can only 3D print something as big as your printer is. But generally, for our needs, that is not really a big problem for us. So we use 3D printing for a whole lot. We print fins, nose cones, altimeter bay, and basically any part that lets us customize our rocket and make it more modular. So on the left is basically the 3D printed parts of our 2022 rocket. Those are the fins and the nose cone. So you can see we have to do a decent amount of post-processing on these parts to get them to a flight-ready state. And that mostly includes a lot of sanding, which Shreyas bore the brunt of, I'm afraid. But we have to sand all those layer lines away to make it smooth enough for the airframe. And that includes the nose cone as well. And then we paint the nose cone. And yeah, that's the process for post-processing. We also round the front corners of those fins, and they have tangs to increase their strength. And on the right, those we did not use in 2022, but those were developments I made later on. And I think I want to share them because just for your reference, I think they definitely help a lot more than some of the systems we had in 2022. So the top left there, that is a modular fin can system. So basically, you epoxy in a set of threads into body tubes, and that lets you have super modular control over every parameter of your flight body. So your fin cans, you can make them tapered like you see in that picture. You can have any different kinds of fins you want, bigger, smaller, forward, farther forward, different shapes even. And you can just swap those in and out by unscrewing and screwing in a new section. And that makes it super easy when you're on the launch pad to account for any changes in the weather or anything you want. Bottom left there is a 3D printed transition. So the problem with the only having the threads 3D printed like we had in 2022 is that sometimes if they're very slightly out of alignment, sometimes they're impossible to thread onto. So if you 3D print the whole transition, that problem goes away. And the only thing to note there is that I would definitely not recommend using plastic as a bulkhead. You definitely want a wooden bulkhead epoxied in there as well, because the plastic can be porous enough for ejection gases to go through to your payload section, which you definitely do not want. And on the right there is a nose cone I designed, also meant to work with the same threads the fin can works with, as well as having a internally threaded section for ballast. So that's designed to be used with ball bearings, for example, where you just put in ball bearings and then you screw in the stopper far enough so that they have no freedom of movement. And it allows for very fine customization of the mass.
Yeah, and one thing I wanted to add, if you just notice, is with this transition section here on this slide, you can see that both sides of the transition section are the same diameter. It's because in 2023, the guidelines didn't require you to have sections of different diameters. So yeah, TARC likes to vary the guidelines from year to year. Now we'll get into some of the launch. So after actually manufacturing our prototypes and stuff, we went and collected launch data, analyzed launch footage, and made engineering decisions based off of those results. So initially, for the motor, we looked at our inventory of what the club had, and also referenced Open Rocket to see what motor would be ideal for the goals we were trying to achieve. And we ultimately determined that an Aerotech F32 motor would probably be the most ideal. So that is what we initially selected and launched with. So here you can see, this was the first time one of our rockets was on a rail in 2022 or during the 2022 season. And one thing you can notice here is that neither section is painted, which is a requirement for your qualification launches for TARC. But in this case, for initial prototype, just to see the flight behavior and stuff, it wasn't important. So I'm going to show a few launches just for you guys to get an understanding of what we were working with, and then we'll talk about some of the decisions we made from there.
One, go!
Okay, so as you can see, I had a pretty straight trajectory, which we were very pleased to see on our first launch. But as we continued testing, hold on. As we continued testing, one thing we noticed is, I'm not sure why that one isn't working, but we have enough clips. So one thing we noticed is we were experiencing some tilt, usually 10 to 15 degrees off the launch rail. So yeah, you can see that in this clip.
5, 4, 3, 2, 1.
Again, similar flight behavior.
4, 3.
So yeah, the main issue with the F32 motor was there was consistent tilt during the launches, and here you can see kind of a screenshot of the frame by frame of some of the launches. And one thing we actually noticed about the flight trajectory was the fact that it would exit the rail, tilt, and then stabilize and continue on that flight path. So we ultimately believed that the possible issue was that we didn't have enough or a fast enough exit velocity off the rail. So ultimately, we decided that we wanted a motor with a faster burn time that provided the same amount of impulse, so that it would have a faster exit velocity off the road. So yeah, looking at the F32 thrust curve analysis, you can see that the burnout for an F32 motor is about 2.1 seconds. Yeah, and like I mentioned, we wanted a motor which provided the same amount of thrust, but with a faster burn time. So we would have a faster exit velocity. Hopefully, that would fix the stability issue that we had. So again, looking at what we had, assessing our possible motors from the club inventory, and also looking at Open Rocket, we ultimately decided that we wanted to try launching with a Cesaroni F70 motor. And here you can see with the F70, the burnout time is about 0.8 seconds, which is much faster, and it provides the same amount, or roughly the same amount of impulse. So yeah, here's the side-by-side comparison. You can see the thrust curves. Yeah. And yeah, here's some launch footage with our new motor.
2, 1.
So as you can see, pretty straight trajectory. And one thing that we were able to achieve was actual
4,
consistency
3,
with
2,
the straight line trajectory.
1.
So straight into the clouds in that one.
4,
And then
3, 3, 2, 1.
yeah, so we were overall really happy with our results. And the other thing that Cesaroni was better about is, given that the nature of these motors is that they're hobby grade motors, we noticed that the Aerotech batch we had, I think it was from 2019, was pretty inconsistent. That's why some of the initial launch was straight, but then we had some tilted launches and then some straight launches in the mix. And we just noticed that Cesaroni's quality control happened to be better. So yeah, it fixed our problem, and the motors were more consistent, so we were able to depend on them and rely on them more. So yeah.
Yeah, and in the chat, that's definitely true. Fighting the weather is probably the biggest problem you encounter in this kind of competition. In terms of how we actually control our altitude, we do it through a mass adjustment system. I alluded to that earlier when I was talking about the ball bearings in our later development, but at this time we were using washers and coins, basically anything circular, so that our center of gravity would stay within that central axis of our airframe, using different components like wood, metal, rubber sometimes for different densities, and that lets us have some pretty decent control over our mass. So here we have plots of all of our launches, and especially launches after nationals. And what we're looking for here is we ran a linear regression, and we are focusing on the slope here because the slope tells us our foot per gram ratio. That tells us if we add 1 gram of ballast, how much lower are we going to go? So on the left, you can see it's about 2 feet per gram. On the right, it's about 2.3 feet per gram. So yeah, that's just a very important metric for us to determine how we're going to set up the next launch. And before you start thinking we're all technical, this definitely would not have been possible without our entire team, without the snacks we brought to launches, and without the 30-foot pole we had to use to get our rocket out of trees at times. So the rocket, with that tilt, obviously did not go straight up and down. Sometimes it went over the river, sometimes it went into trees. And it was really thanks to our team and all of their hard work that we were able to recover it so many times and be successful in the end.
Yeah, so ultimately, we ended up qualifying for nationals. The process for qualifying for nationals is you find a NAR adjudicator, and they come to your launch site. In this case, our mentor was actually a NAR member who was eligible for this. So Bruce Buswell was our kind of adjudicator. And basically, you have 3 launches. You declare it's a qualification flight before you launch, and you launch it. and then your two best launches are submitted. I think it's by like the first week of April, roughly. Um, and you're basically stacked up against around 700, 800 other teams. And the lowest scoring 100 teams make the national finals. Um, so yeah, normally, usually like under 50 points for your two launches together will kind of you'll most likely make nationals. So um, I forget exactly what our score was. We tried finding it, but we didn't have any documentation on that. But yeah, now we'll get into kind of nationals and the summary of our launches there. So yeah, um, with that being said, our first launch during nationals, we were expected, as Vanu mentioned, you are expected to reach two altitudes. So in the morning section, we were expected to reach 810 feet, um, and we ended up reaching 808 feet. And we were within the top flight duration window, so there was no or point additions there. So we had a 2 point launch. And for our second launch in the afternoon, basically the teams, I think it's the top 50 teams from the first like morning block, they moved to the second launch, and basically we were expected to reach 860 feet. We ended up reaching 849 feet, and we were able to stay within the flight duration window. So we ended up scoring 11 points, and cumulatively we scored 13 points. Oh, and one other thing I didn't mention, the national finals is in the Plains, Virginia, which is Northern Virginia. It's like an old horse racing, or no, it's a horse racing facility that's still used for that. But yeah, it was a really cool experience. We went to DC and we were able to, yeah, have that experience. And
Yeah,
another thing
and
I forgot to mention is, sorry, one second. The weather that day, I would say there is a slight element of luck because there was wind, and a lot like rain at some points during the day. So basically, you were told when to launch and you launched, but you know, we ended up being lucky and we caught like a calm moment when our we were told to launch. So that ended up playing in our favor and had us have two successful launches. So yeah.
yeah, and looking at these numbers, you might think, wow, everything must have gone perfectly while they were there, huh? But that is definitely not the case. So we were in our hotel room, right? The night before these launches, we had just gotten in. It was like 2, 3 a.m. something, and we're taking stock, checking our inventory of all our stuff, and we discover we don't have our payload section. We only have our backup payload section, which does not have hard stops for the egg casings. That basically we took some couplers and we epoxied one set into the bottom of the payload section and another set into the top of the payload section that the egg casings slot in between. And that stops the eggs from moving around and obviously breaking. And that's a big problem if you don't have that. And our backup payload section was essentially just the tube of the right length. So what are we going to do without those couplers? And we are 2,000 miles from home. We have basically no supplies. We have like one X-Acto knife and some masking tape. So we're looking around, and we see a toilet paper roll. And hey, that's cardboard. It's circular. So we take our one X-Acto knife, we slice up that cardboard toilet paper roll, we open it up, put it into our rocket, and masking tape it up. And honestly, it worked. I mean, it was definitely not perfect, and the eggs probably had a little bit of wiggle room, but with what we had to do what we could, and definitely the ability to think on your feet and adapt to a situation where you have imperfect tools, items, your rocket. That is definitely something you need because if something can go wrong, it will go wrong.
Yeah, so ultimately, we ended up winning the competition with our score of 13 points. And the second team, which came from Newport High School, ended up winning second place at the competition, which made us the first school in the American Rocketry Challenge history to win both first and second place. And we took home $35,000 in prize money. And yeah, it was really overall awesome experience. and a testament to the fact that our club, is not only just the teams and how supportive we are amongst our teams, but we also shared resources, knowledge. We were very collaborative within the club amongst all teams so that we could all succeed together. So.
Yeah, so after we won the national competition, there were some pretty cool opportunities. That includes our achievement was read on the congressional floor, which is pretty cool. And we had the opportunity to meet Congressman Adam Smith. And we also had the opportunity to present in front of the school board about basically our experiences and how we got there. And that basically got us the opportunity to advocate for some STEM facilities, for more professional STEM facilities at our school as well.
Yeah, and here you can see on the left rocket was the second place team's rocket, and then the right rocket was what we used to win the competition. So, yeah. Yeah, and with that being said, another prize of winning the national competition is the all-inclusive trip to the international rocketry competition, covered by Raytheon Technologies. So, you may be wondering how the IRC works. So, the International Rocketry Challenge is a competition between the winners of various national competitions around the world, and it's hosted at the Farnborough International Air Show in even years and at the Paris Air Show in odd years. So in 2022, it was at the Farnborough International Air Show, and yeah, we competed against the United Kingdom, Japan, and France. Um, yeah, yeah, and then with the competition requirements, it's the same rules as ARC, so it's back to the qualification target of 835 feet. And with that being the case, it made it easy for us because we already had launched a lot for that altitude. So we kind of just designed our rocket with some added style points. So we just made a new rocket, added some US style to it, and yeah, we did some launching before July to kind of just make sure that the newly manufactured design was working well. How do you want to?
Yeah, here's just an example of one of our international flight
Two,
launches.
1.
Here we go.
Yeah, that one's a pretty nice flight. Yeah, 60 acres, soccer games, all the time. We definitely had to reschedule a few launches because of that. Getting motors to England. Yeah, so we shipped those to our hotel, I think, right?
Yeah, we used Aurora Flight Sciences, I think. Like they have some I think NAR has some ties to them. So John Hockheimer, the president, he coordinated with Aurora Flight Sciences to kind of support the shipment of our motors to England.
Yeah, yeah. At the IRC, there's only 4 teams, right? So they're able to really give you a lot of support in making sure you have all your tools, basically.
Yeah.
2.
Yeah, and then beyond the actual launching, we didn't. Well, me and Vanu couldn't find any launch footage of the actual launch we did at the competition, unfortunately. But overall, it was a really cool experience. We had the opportunity to meet Matthias Maurer, who is an astronaut for the ESA, and also, given that Farnborough International Air Show is a trade show, we had some time to go walk around and just see like what is at the forefront of the aerospace industry right now. And that was a really cool experience because we're all very interested in aviation and space too. So yeah, all the big companies were there and they had booths and actual like tech, like, displays and stuff out, which was really cool. And then, yeah, we ended up placing second at the international competition. And here's a photo with all the teams. So we were the biggest team by far. And then you can see the people in the black jackets, that's the UK, and then the orange shirts, that's France, and then the white jackets is Japan.
Yeah, so we just wanted to give a little update. What are we up to now these days? So at UW, I am on the Formula Motorsports team, and we design and build a F1 style race car to compete in the Formula Student competition. And um, yeah, that's last year's car at the bottom there. And with that car, we actually placed third in North America. And my project on the team this year is designing and testing a custom cold plate for our inverters. And I'm also part of the Husky Satellite Club, and we're designing a CubeSat for hopefully a 2025 launch. And it's sort of a proof of concept for a much farther in the future moon orbiting CubeSat, probably in like 10, 15 years or something.
Yeah. And then at Georgia Tech, I'm part of the Experimental Rocketry Club, where I'm an avionics team member. And I also am currently doing research with the Benties in Combustion Laboratory, researching ammonia combustion as an alternative fuel. So a little bit more about my projects with GTXR. Basically, I worked with the avionics sub team on a mission control system. So taking the telemetry data from various onboard systems, reading them on a computer, uploading them to a SQL server, cleaning the data and uploading it to a SQL server, and then using Grafana to visualize the relevant data in a nice, clean format. So as you can see here, this is like kind of just a mock-up of how it looks. And then we also have been recently conducting some tests with featherweight altimeters like tied to drones flying around campus just to see how the software is responding to that. And then with the Benties in Combustion Lab, I'm working under a PhD student who is researching ammonia as an alternative fuel. And here you can see on the right, this is an ammonia flame, and there's a probe in the quartz tube. So right now we're doing atmospheric testing, just seeing how to optimize to lessen NOx emissions. And in the future, we will be conducting a high pressure test later this semester. There's some stuff that we have to machine so that we can be readily equipped to do that. Yeah. Thank you so much for having us and taking the time to listen to us. We also wanted to extend our gratitude to Bruce Buswell, our mentor throughout high school. He has been an amazing mentor, and he knows a lot and is really supportive. He's always ready to help. And yeah, in general, just thanks to the American Rocketry Challenge for providing us with relevant STEM experience in high school. I'd say that STEM curiosity that we've all experienced was definitely kind of intensified by competing in this competition and has definitely set us up for success in college. Vinu, do you have anything?
Yeah, and uh, probably not a lot of you are middle and high school students, but even if you're not, you can still get involved with the American Rocketry Challenge by mentoring a team or volunteering with the competition. And I think both of those are really great ways to get more involved with this community. And yeah, it's just a great opportunity.
Yeah. With that being said, here's some of our contact information if you guys want to reach out to us or stay connected with us. But any questions about our presentation or anything like that, feel free to ask them in the chat and we'll do our best to answer them.
How many practice before quals? I'd say probably somewhere in the order of 20-ish,
20, 30.
20, 30. Yeah.
Yeah.
Yeah, we try to get it pretty dialed in.
Yeah, usually when it came to qualification launches, we kind of started the day off. We didn't go in saying like, okay, we're gonna qualify, but it would be like we had consistent good launches. We're like, okay, this is a good day, so we are going to qualify now, or have a qualification launch, and then we would kind of just declare that and have the launch. So yeah, that was kind of how we went about that. Any other questions?
Yeah, we placed second at the international rocketry contest.
Cool. Well, I mean, yeah, thanks so much for taking the time to listen to us. I guess if you guys have any other questions or want, oh, there's another question that came in. Air
Yeah,
temperature.
yeah. So air temperature, we consider that, but um it's very small compared to the amount that like wind or other bigger environmental conditions can impact our flight. So that was less of a empirical uh, data-based adjustment and more of a what are the vibes seeming like adjustment. So we did take that into account, but honestly, that doesn't affect it beyond a few like less than a gram of change with our ballast.
Yeah, and the more noticeable thing I think was just like there was like when it was hotter, there would be updrafts, which would kind of impact our flight duration. But you know, we didn't qualify on like days when it was too hot or anything. We usually in Seattle in like February, it's pretty cold anyways, and it's overcast. So I mean, it was pretty predictable weather and updraft or any of those like consideration factors were never really an issue. So.
What would we do
What would you do
differently?
differently?
I think I think differently, probably more 3D printing is like I was talking about, I showed some more designs, and those can really help to decrease the cycles in between launches. Like for this design, the time it takes to like take your rocket apart and then uh, repack the parachute, drill the delay, uh, eggs, ballast, all that, probably, what would you say, 30 minutes in between launches, 30, 40 minutes?
Yeah.
Yeah, and if you have a more modular system that's achievable with 3D printing, you can really take that down to 15, 20 minutes, honestly, if you just uh yeah, unscrew, rescrew. Yeah, makes it a lot easier.
Yeah, adding on to that, I'd say like one frustration we had is like there was many times where something would break or something would happen to the rocket, and we would just be forced to like close up shop and head home for that day. And it's like 60 acres is kind of it's a drive. It's like 20 minutes from where we are. And also like we're all like going at an early time on like a Sunday. It's like we want to get some meaningful like work done. But having that modular system where we were able to like rapidly prototype on the field and make these replacements really quickly was very convenient and kind of like helped remedy that frustration. So
Yeah, so about fins, uh in previous seasons before we won, that was definitely an issue. Um, but switching the printing orientation to starting on the leading edge definitely helped a lot. And also, we switched to printing things out of PETG for the most part rather than PLA. And PETG is much, much less brittle than PLA. So it helps to absorb that impact a lot better. And we and we were actually, I don't think we had a single 3D printed part break that season, except when a nose cone landed on gravel and that did break, but that's a rare occasion.
yeah. Um, Yeah, any other questions? I mean, one thing I wanted to say earlier, we're still happy to answer questions. Our time slot is, we still have some time, but feel free to reach out to us about anything related to the competition or our work with it, to our emails, or you can connect with us on LinkedIn. We're always open to, you know, communicating with you all. So, yeah.
Oh yeah,
Cool.
for
Well,
longer
in that
rockets,
case, oh, go ahead.
yeah, longer rockets I think do fly better, just because they're able to cut through the air better. Like when you think of a canoe, they're very long and very thin, and they're able to cut through the water. And it's a similar sort of principle for rockets in the air. And you really want a length to diameter ratio of probably 15 or 20 to 1. And yeah, I think that's probably ideal. Obviously, if it's too long, it'll start bending and tilting. But yeah, definitely significantly above the minimum length is a good thing.
Yeah, I'm putting our contact information in the chat right now. The other thing, which, more than flying better with the length, Vanu mentioned it earlier, but it added some more wiggle room for us with the CPCG. It provided us some, just flexibility with that if we wanted to change anything, which was an added bonus.
Yeah, yeah.
Cool.
Yeah, cool. Thank you guys very much for your attention and listening to us. I
Yeah.
think that about wraps it up.
Yeah. In that case, I guess we'll stop the recording. Yeah, thank you so much for taking your time to listen to us. We were really excited to hear that, they wanted to have us, that NAR wanted to have us come and speak about this because it was a really fun project and ended up turning into some nice achievements as well. And we all experienced the ups and downs together. So it's really fun to, talk about it and share our story with you guys. So.
Yeah.
Cool. Take care, everyone. Thanks.